We'll get started now. So today we're here to talk about Adopt OpenJ9 and the possible improvements you can get when running a Spring Boot application just by the easy switch of your JDK. So my name is Charlie Gracie. I work for IBM on the runtimes team, actually as a committer on the OpenJ9 project. And today with me, I'm also co-presenting with Michael.
Hey everybody. Ooh, still kind of loud, I guess. I'm taking a picture because I forgot to do that when Jamie and I did our lab on Tuesday morning, and I was berated by not having a social media presence. So I'm Mike Thompson. I'm on the WebSphere development team. I'm an architect and an offering manager, so I straddle both the technical team and the business team. So here I am.
All right, now I've got the handheld mic, so if I move around and it's not there, just wave at me and I'll try and adjust it to make sure everyone can hear. All right, so quick outline, the things we're going to cover today, sort of economics of cloud, Java in the cloud, some demos to actually put some real world examples to what we're talking about, so you don't have to take our word for it, you can see it happening live, and then some wrap up. So part one, in the cloud, really the whole rule for everything is you pay for gigabytes per hour. So it's not this normal world for most people. Any real small change, increase, decrease, can be real impact on the dollars you spend for running things in the cloud. Basically every provider you go to, you can pretty much look up their gigabytes per hour. Sometimes it may not be based on quite gigabytes, they have different sizes and amounts of memory, but that's pretty much the true cost for a lot of the things you run these days. So the myth that's always been around in the last at least 5 or 6 years is that you have basically an infinite amount of RAM. Doesn't matter, you're running your on-prem servers, throw another stick of RAM in there, you got a terabyte of RAM, use it all. So lots of actual applications have been written not to care so much about the amount of RAM they're using, but rather CPUs. So there's kind of, we have to deal with this sort of myth now about the way that your systems are going to be set up for doing a lot of your runs and deployments. So the actual reality is it's very important to measure your memory footprint, and the easiest thing you can show to your boss is we now went down to a lower tier in all of our cloud deployments, and here's an actual dollar savings we're going to save every month or year for the company. This is basically because of the trend of virtualizing everything. So the big servers that used to be 100 CPUs and a terabyte of RAM are now sliced to 2- and 4-way machines with 64 megs or 512, or depending on which bracket, 1 gig of memory that you have. And as you move towards more of a microservices environment and even further on to functions as a service type workload, really what you see is the overhead of actually starting up a JVM, the actual runtime footprint of the JVM itself, now starts to really be something you have to measure and pay attention to, because instead of having one JVM that runs all of your application, you now have the JVM overhead for maybe 100 JVMs, depending on how many different services you have. So just one distinction I want to make, sorry if it's really low, the on-disk size of your application is really only that important to the cloud provider itself in terms of the space they have to have. It's your physical memory that is that's being used is really relevant for your application costs. So this is sort of an example of what this means for a lot of people, is that if you have this leaky faucet, you will waste gallons and gallons, thousands per a year. Leaking a few bytes as you're running in your application may be something you have to monitor now as you spin up and deploy and scale out, and you have hundreds of different VMs running different microservices. You may really have to pay attention to these small leaks or overuse of memory that you had in the past. So what does this mean for your cloud developers? Changing the XMX, which is the heap size for your JVM, can have really major impacts on your business. And it's something that's very easy for people to understand because it impacts your bottom dollar. So what this means is you're going to actually try and work into smaller heap sizes for your application, or pick VMs that by default sort of do different size heaps or have different amount of memory they require for their off-heap sort of metadata. and you're going to need to understand where this memory is going. So there's going to actually be probably a lot more tools involved, and you're going to have to do a lot more analysis that you might not have had to do in the past, because it's really prevalent now and important that you go and do this work. Again, and the big scale out factor is really where it's going to matter in a lot of these cases. So what's the reason I'm here for today? OpenJ9. OpenJ9 is a completely open source JVM that was opened and released, or donated, I guess, to the Eclipse Foundation last year in September in 2017. It's actually released under the EPL v2 and Apache version 2 license. It's a very open community, accepting pull requests and changes from everybody who makes them. So we'd really like to see anybody who wants to be involved come out to the community and look us up. OpenJ9 itself is just the virtual machine. You have to have the whole JDK to go with it. The best place to go get JDKs these days is to actually go to Adopt OpenJDK. If you're not aware of it, it's a community build process run by the London JUG. They actually are producing OpenJDK binaries for OpenJDK with HotSpot, OpenJ9, and any other vendors are welcome to come and bring their VMs and have it built and tested there. So it can be a very easy place for you to know what your binaries actually contain. And with all of the builds they do, they also have a Docker Hub account, so they have Docker images for every build they do as well. So you can go and base your Docker image on top of one of the Docker images from Docker Hub for Adopt. So everybody's favorite phone from the 90s, indestructible. Everyone had one, I hope. The reason OpenJ9 is a very good fit for the cloud, as I'll talk about in the future, is it actually has its roots in ME VMs. So Java ME was basically the first full support that we had. There's some people here in the room that also worked on it back in the day. So that's why we are there. And in the ME days, small footprint was really key. Those small phones didn't have much memory. Sometimes they had a lot more ROM than RAM, but they were very small amount of memory, so you had to work in these small environments. You need a quick startup. It was mostly used for games. If your game took 2 minutes to load, you're not playing the game very often. And you also didn't want your game to get quicker the more you played. So you would want it to be a very sort of consistent startup and a very quick or immediate ramp up as well. So that's one of the distinctions I'll talk about as we go on, is the difference between sort of startup and ramp up. So again, in the cloud, the titles are basically the same. You want a small footprint to save you money, and it also saves your cloud providers money. More density on their machines means they need less machines to serve everybody. Faster startup, because when you scale out and you spin up a new instance, you don't want this instance to take 2 minutes to be going. You want it now because you have the demand of scaling out. So a quicker startup is better. And again, for ramp up, since you're paying per gigabytes per hour, if it takes you 5 minutes to complete the transaction instead of 2 minutes, you've now just wasted more money. So a quicker ramp up to getting to where you can have things completed quicker is also very valuable. So why is OpenJ9 better? In terms of Java heap and garbage collection, out of all the JVMs out there, OpenJ9 has the smallest objects themselves. There's lots of metadata associated with Java objects that the garbage collector imposes on your objects in your runtime, and we have the smallest sort of extra footprint on those objects as one of the reasons we can keep smaller heaps and provide similar perf. And a lot of other areas for our internal data structures, we use a lot of very compact data structures that we've done that came about from having to run on these ME phones back in the day, and we aggressively use less heap. There's a trade-off between how much heap you have to how much interference your GC provides. Bigger heap means less frequent GCs, but we've really tried to keep our heap down where you need it so that you're paying. There's a lot of things you can tune, but as long as you're spending less than 3% of your total time in the GC, we probably won't expand the heap. just to keep it low and use less memory for you. Another technology that we have is shared classes. This technology originally started just for sharing class data, but it's grown into a bunch of other areas now, which I'll talk about shortly. But this is an option if you're using OpenJ9, you should probably just enable. In the next release, you won't have to enable. It'll be on by default in Java 11 and further after our next release. We're just working on that now. And there's a size for the cache. Because it does increase your on-disk footprint, we have an option so you could control how big that is. So what shared classes really is everyone's aware of your Java class file for running Java. A large part of that class file is actually never changes at runtime. So back in the ME days, when I mentioned there used to be lots of ROM compared to RAM at times, we decided that we were going to divide the class into two pieces. One that you could burn into ROM on the machine, and then the dynamic part that would change during runtime. So we then have this two parts of the class. When we load a class, we create a ROM class and then a RAM class for all of your dynamic data. But since this ROM class could actually be burned in ROM back in the day, we can actually share this data across VMs, and then we don't have to, or we could store it in this cache where you don't have to load it in the future. So one of the big benefits is that you'll see in the bottom here, all of these classes, all these VMs have the same ROM classes, so you can actually pull them out into just a single cache, and that saves you the footprint per instance, which in Docker environments you can actually mount you can mount a volume so you could have this shared across different instances if you want it in that sort of scenario. But then you get this faster startup because you don't have to load the classes, and then you have your smaller footprint. One of the benefits then that we have this shared piece of data is we started putting our AOT code, or we start ahead of time JIT code. So instead of letting the JIT have to gather data at runtime and go compile your code, we actually will store this code from one run into the cache. So the next run that you have, you actually just load this data right out of your cache and use it. So the distinction really that you have to be aware of when using shared classes is when you have a cold cache or a warm cache. A cold cache has no data in it, so when you run against a cold cache, it is probably a little bit slower than normal because you're actually populating the cache as you go as well. But then once you've run one time, you now have a warm cache, and all of your data will be there for the next run, so you can see some pretty significant startup improvements. And it also removes your compilation time as well, so you get it earlier in your runs. A few extra options that we have that also a lot of people use in cloud environments is Quick Start. That will actually start your VM up in a much quicker way. It's just a bunch of tuning options, changing some of the options for how fast we compile or when we compile. But with that, it's meant to speed up your startup and best used for short run applications. So your peak throughput might drop if you enable this, but you will be started up much quicker and get to the main part of your application quicker. And then we have another option called Xtune Virtualized, and this basically sets all kinds of flags for being even more aggressive when we recognize that we're in a Docker container or other types of containers. So more aggressively give memory back when the heap isn't being used, and all kinds of these extra features. It recognizes when you're idle. So if your application isn't being used, well, let's actually shrink your heap down right to your live set size and give that memory back to the OS so it could be used for other instances. And then if you ever need to come back and this instance gets used again, we can just expand the heap and keep going. So you'd pay a little bit of penalty at that time, but you get to give back all of this memory. This, again, is another option that was just enabled by default, was recognizing you're in a container and doing this for free for you in the last release. So if you pick up any JDK 11 builds from Adopt with OpenJ9, the latest ones all do this for free for you in the Docker environment. All right, so we're going to now switch to part 3 with the demo.
All right. So I am going to take over, and I'm going to actually show you all the stuff that Charlie just talked about in practice. So you're here because you want to learn about Spring Boot and OpenJ9. So let's actually get into some Spring Boot stuff. As Charlie already covered, there's some pretty significant benefits. All of these apply to Spring Boot. Number one, it's really simple to adopt. You go to adopt.openjdk.net, you download it, and you use it, right? By doing that, you get a smaller memory footprint, higher throughput, faster startup. There are things you have to be aware of. Because it is a different virtual machine, right? It's different from HotSpot. If you're doing any sort of tuning and setting HotSpot-specific flags, those will not apply to OpenJ9. And it does have a different GC algorithm. So as always, you want to do your own testing. You want to validate everything we're up here claiming about. But in our observed practice, it is a far better JVM than HotSpot. So how do you get it? Well, go to openjdk.net, or you can use some of the Docker base images out there on Docker Hub, and that's what we're going to be doing here in the demo. To use it, download it, set your Java home, set it on your path, java-jar, right? Super simple. Or in your Docker file, do a from, and let's actually jump into a live demo. Ooh, live demos. That's why I put the little fire things up there, because it's all local, but it's still going to blow up, because, you know, demos. All right, so what's relevant for the demo? So we have a Docker file that we're using for this demo. It is based on builds from adopt. It will basically grab all of the things that you need. It'll do a get clone inside the image. It'll build out Spring Pet Clinic, and it'll run it. So it's self-contained. We're going to compare and contrast an OpenJDK 8 build, which is using HotSpot, with OpenJDK 8 with OpenJDK 9 or OpenJ9. So let's actually go over and do that. All right, so what I have running here is Docker stats. If you're not familiar with this is, it's basically top for Docker. It's going to show you, your CPU, your memory utilization, what have you. And on this terminal window down here, I'm going to run my HotSpot built Docker image. I'm not going to subject you to doing a Docker build. That would be insane. So that's going to come up. We got live stats. There's my pet clinic. It's running. And if I am so inclined, I can actually, that's the wrong window. Boop. Boop. Now I can hit pet clinic. Hey, look, it's up. New tab. It's all there. I can click around, real running code, huzzah. All right, so now let's do the exact same thing with OpenJ9. So my image is going to start up. It's going to launch Pet Clinic. You can see that, that will, respond once the application is actually up. There we go. So there's my Pet Clinic running, and this now in OpenJ9. But notice the difference. The memory utilization for HotSpot is sitting at 455 megs. And all I've really done is started the JVM and hit the front page. Compare that with J9, which is only using 160 megs. The only difference in these Docker files is the from line. Let me see if I have that up really quick. Just to prove it to you. OpenJDK, Docker file, OpenJ9. That is literally the diff between those files. So doing nothing other than changing my from line, I have significantly improved my performance for my Spring Boot application. I've cut the memory usage by, what is that, 60%? So really, really easy to do. And we totally encourage you to do that. If you're running this in a VM where you're actually invoking the java-jar, all you need to do is grab OpenJDK, put it on your path, and start using it. It's that easy. Yeah. CPU usage is much higher right now. I'm not sure why, but I'm going to throw you a shirt because you asked a question. So good job for that. Normally when I run this, and this is always the curse of the live demos, HotSpot is usually sitting at a higher CPU utilization. So I'm not sure what I did differently here, but over time that will mellow out and it'll behave better. Oh yes, good question. So let me see if I can find it in the logs. So here's OpenJ9 and here's HotSpot. So OpenJ9 starting a little bit slower. That could be because I started it after, I'm not sure. But you asked the perfect question, because if I go back to my slides, let's go faster. I did not put him there. I'm not paying him $20 to ask me these questions, but it is the perfect question. So Charlie talked about X quick start and shared classes, right? So just as a super quick refresher, there's some arguments that we're going to add to the Docker file here. Share classes, that enables the cache. SCMX, which sets the size of the cache, and we're going to set the quick start, which is trading off faster startup for slower throughput in the end. And I have some charts to show you later about how that kind of balances out and what the actual impacts are. So now let's look at the Docker file. So same from line using OpenJ9. This mess of a bash command that is in green here, this is where we run the app during the Docker build and then kill it. Well, we ask it to stop gracefully with a hang up. And what that's doing is that's starting the JVM, that's warming the class cache, and then shutting the system down and then taking the snapshot of the Docker image so that the subsequent startups are faster. And then, you know, at the bottom, I've added those arguments. So let's see what that looks like. So if I go over to my, the CPU's fallen. Oh, thank you, Jamie. So I told you if you waited long enough, it would come down. So yay, I wasn't lying. So, pardon? You're asking why the CPU utilization has fallen? Do you know why it was higher than then dropped?
Usually when it first starts up, that might have been things that were still queued for the JIT compilation to happen, or we have other threads that are looking. The actual idle detection that we use to detect we're idle also consumes some CPU until we decide we're idle, checking things. So yeah, there's a bunch of things that are actually looking for these different state changes, and as they happen, they will consume CPU, but eventually it does settle down.
Right. And Jamie is a plant, so good job, Jamie. You did your job. All right. So now I'm going to start a third Docker image. This one is Pet Clinic with OpenJ9, and this one is warmed, right? That had that crazy bash line that I had in there. So if I bring this up, and don't touch it, assuming, you know, all the gods are good, this will start in about 6 seconds, which is, you know, half of what the other JVMs were running. Okay, yeah, 6 seconds, total JVM runtime 7 seconds. Why does this matter? Well, we're talking about Spring Boot. Spring Boot is often very popularly used for microservices, and one of the characteristics of a microservice? Rapid scaling and shutdown, right? You want to be able to get to being productive as fast as possible if you have a workload that has that kind of characteristic, right? If you're running a batch processor and it's running 24/7, these don't matter. But if you're running a highly scalable, short-lived process, this stuff really matters, and it will save you money in the cloud, no matter what cloud you're using. So that is basically the proof in the pudding that we wanted to share at this talk. We've got, oh, let me go over here just to show you. The memory usage on the warmed one is also a little bit lower, and that's because we didn't have to go through the, you know, the JIT and all the warming, because we already did that. So if you have microservices and your services are short-lived, these are really, really good options for you to use. And again, all you have to do is download it. I don't know if I can throw a shirt that far, so I'm going to have Charlie run it back to you, but go ahead. That's a great question. I'm going to kick that to Charlie, because I'm not exactly sure. The block I/O, do you know what the difference is, or what's causing the difference between HotSpot J9 and the warmed version?
The warm one at 200 megs. I think the difference there, is because we end up doing a big read from the shared classes cache to map all of the data in. But I'd have to look that one up. I'll get back and I'll tweet about it after the talk once I've asked somebody who knows for sure. But I'm pretty sure it has to do with mapping the shared classes cache.
Okay, cool. All right, so a word on Docker layers, or why you should never do what I just did. This is my Docker file. This is a really, really stupid Docker file. And Heiko's shaking his head. I was like, yeah, that's a really stupid Docker file. It's perfect for demos, right? Because it's totally self-contained, but it's terrible in the real world because what I'm doing is I'm installing a whole bunch of stuff I really don't need for the application. I'm doing the build for the application in the container, and all that's ending up in my final image. Yeah, you have to do those steps at some point, but you should really be doing them somewhere else, right? Either in a build pipeline on your local process, whatever. This is simpler. This is, basically what Spring.io had been advocating for, is like, this is how you build a Docker file. And that's great, but this is better. So I'll explain why in a sec, because wait, didn't you just tell me lots of layers were bad, right? I mean, if we go back, I'm like, doing all this stuff, it's populating it, there's so many layers, size, it's terrible. Well, these layers, forgot I had this slide here, so I don't went back for no reason, but these layers are not helping the app at runtime, right? I've installed a bunch of tools that my app doesn't use at runtime. I've cloned the source, which my app doesn't use at runtime. There's a whole bunch of stuff in the image I don't need. We want to create a lean image, and we want to do that, if we can, in a way that's pretty smart, so we can have better builds. So this has actually now been updated on Spring.io to show how you can create a multi-layered image for your Spring Boot application. And the reason this is good is because when you build your application and you rebuild your application image, right? The simple way of just slapping the whole jar in there, what ends up happening is you change one line of code, oh, I had a typo, or whatever, changed a message, added some logic. That entire jar is rebuilt, and that entire jar layer is rebuilt. Spring Pet Clinic is like 30 megs. Okay, that's not that bad. But in a real world, you might have 100 megs, 200 meg jar file. That starts to get pretty hefty. And if you're having to regenerate 200 megs every time you change one line of code, that's kind of dumb. So what this structure does is it takes the underlying layers that you very often don't change unless you're changing your dependencies, puts that in a layer, and then it reduces the amount of stuff that you have to layer on top, so that ultimately your classes, which is really what you're changing, that's at essentially the second to last leaf layer. So it's when you do those rebuilds, you can reuse the cache. And that's what this looks like. So I'll spare you from doing a build in real time. You can follow the instructions for this lab whenever you want, because it's up on GitHub. But what you want to look for in your Docker builds is this cache reuse. Docker is extremely efficient if you let it be. So this is all about building images that Docker can do quickly. Docker can be efficient. It lets you rebuild faster. It lets you do faster deployments. And critically, it lets you use less Docker repo space because, again, cloud cost. All right, so how do I get there? Well, don't include the build of your application in the final image. That's like really dumb. So you can either build it in the host OS or use multi-stage Docker builds. Those are pretty slick things. And you really want to think about your layers. You want to have as many efficient layers as you can. The guidance up on Spring.io is really good. It's not applicable to every application, right? If you're rapidly changing, I don't know, like web front-end pieces, but you're barely ever changing your classes, you might want to rechange your application layering. So how you're going to do that is going to be different for your app. It's going to be different for your runtime, right? Tomcat, Liberty, whatever. So we've started a project in the open source called the Boost Maven plugin. And the whole idea is it will help you build Docker images that are at least somewhat intelligent fairly easily. So here's your POM XML. You just throw in your plugin configuration. And then from there, you can just invoke it and say, do a Docker build, please. And what the result is at the moment, it will produce an Open Liberty with OpenJ9 based image with your Spring libs at the bottom, your other libs, and then ultimately your application class at the top. So similar to the Spring.io approach. The nice thing about this is, though, you don't have to think about creating the Docker file. This will generate an opinionated Docker file for you. So all you have to do is modify your POM, do a build, and boom, comes out in the other end. And you can actually then just configure your plugin executions so that With the Maven package, you just produce that by default. So let me show you that real quick. All right, where am I? So here's my pet clinic. This is literally, I did a similar demo at Spring 1 a couple weeks ago, so I'm reusing that, sorry. And just to sort of show you here, here's my POM XML with Boost configured, and hopefully that's somewhat readable, and then my Docker goal. So if I do a package and skip my tests, that'll go through, it'll do all the normal Spring build stuff, and then you're gonna see it actually invoke the Docker build process. And I'm pretty sure we just reused the Spotify Docker plugin as part of this overall flow. And that'll get there in just a sec. Okay, so here it's starting. We created a Docker file because I didn't have one. And it's gonna start building stuff, and because I've already done this, it's gonna use the cache, right? Those are all that cache hits that you wanna see. Out on the other end comes a Docker file or Docker image. I can query my images, and it's somewhere in here. And then I can run it. Docker run, map the ports, because I think it's 9080 in this example. And if that all works, oh, you can see Open Liberty starting there in the background, and then Spring Pet Clinic's gonna come up. I can actually hit 9080. There we go. And hey, look, it's up. We did this with Spring Initializer at the Spring 1 conference, and then took that Docker image and pushed up to Kubernetes and did some whole cloud stuff. But with this network, I'm not going to try that. All right, so let's wrap up. So the takeaway that we really want you to have here is adopting OpenJ9 is really, really easy. If you're already using OpenJDK, it's just changing which binary you download. If you're using OpenJ9 out of the box, you get less memory usage. My charts are out of order. So you get faster or less memory usage with OpenJ9 out of the box, no configuration needed. If you want that faster quick start, you can throw on those arguments that we showed earlier, right? That'll reduce your startup time somewhere in the order of 25 to 50%. Right? Results will vary, but it's reliably faster. And then as a point about the virtualized environment, OpenJ9 actually triggers fewer wake-ups so that your workload is lower CPU utilization like we eventually saw, and it's a little bit nicer for virtualized environments. So this is the sort of chart we have for ramping up. The green line is with that Xtune virtualized, right? That's where we're trading off really fast startup time and reaching maximum throughput quickly for longer life max throughput, right? So you can see it doesn't reach as high as the blue line. The other thing to take away is the blue line, which is OpenJ9, gets to max throughput much, much faster than HotSpot. And all of this is because of the stuff Charlie was talking about, where J9 came from that very resource-constricted environment where you needed to start as fast as possible and stay there. So that's all of the good charts, the good stuff. We're going to upload these charts to wherever it is. We're going to upload these charts, probably the conference website and SlideShare and all of those things. But at the end of the day, right, as the industry moves more and more and more to hosted cloud, you really need to be aware of your resource utilization, right? And OpenJ9 is a really easy way to get a lot of bang for your buck. Hopefully that translates. So with that, I'm going to wrap up our talk, and we have probably just a couple minutes for questions. One question, yeah? Sure, so how do we achieve the faster startup with the green line? The memory saving. Sure.
Yeah, so the biggest one just in those footprints is, for the most part, on something this small, is going to be a combination of two things. So it'll just be that we use a much smaller default heap size just to start. You could probably tune some other virtual machines to get closer, but just by default, out of the box, we use a smaller heap. But one of the big ones on something this small is actually a lot of the off-heap metadata structures that the VM and GC uses to be able to do GCs and track other things. We just use a lot smaller. From my experience, those tend to be a lot smaller on heaps for OpenJ9 than compared to other VMs. So like things like our mark map and card tables and some of those other data structures that we use tend to be a smaller or more compact version, or we share them for two different operations where other VMs don't.
All right, last question in the back, and then we'll have to stop the recording, and you guys can just talk to us up at the front. So.
What's your take on the Graal VM efforts and these native image compilation compared to the stuff that you're doing?
Sure.
I hear people saying, yeah, for startup things and improvement JVM, they don't matter anymore because you just compile stuff to native images for these functions and so on.
Right. So to repeat the question. Sure. So to repeat for the recording, and then I'll throw it to Charlie, is what do we think of the Graal and direct native compile and those kinds of things?
I think it's a great direction for everyone to be going into and looking at. Having sort of an instant on is definitely on our roadmap as well. If you look, so a lot of the OpenJ9 code base is actually based on another open source project we have called OMR. So where we kind of like pulled out all of our language agnostic parts of the VM and made another project. The compiler in there already also can compile a bunch of code out to dwarf files that you can just link into an executable if you had a smaller runtime as well. So that's also a direction we're looking at. And then for other areas as well, just recently people have been talking about and pushing a lot of code for our JIT as a service story. So you can actually offload a lot of your compilation onto another server. But since you're actually offloading this and keeping caches around on the server side, you can then still turn around and then also hopefully be able to use that into JIT caches or do more things like generate some object files you could link into applications as well. So I'm glad a lot of the different VMs are out there also pushing the envelope in different areas, because then competition is great for everybody. So the more competition, the more it drives everybody to do those types of ops. And I think we'll be along some sort of comparable area for that. May not be a complete native image, but we'll be doing something to try and get to that type of thing.
Awesome. Thank you, Charlie. So we'll be up here if you have any further questions. If you didn't get a shirt and you want one, IBM booth right outside the theater. Thank you, everybody.